I guess after a bit of a breather, we can jump back into um, lots of topics that are remaining. We have basically, what, 6 lectures left. And I think mainly the topics that are remaining to cover um, are somewhat related to the review session that we did on Friday, um, where we tried to set up approximate solutions to these mechanics problems. So what I'll do today is very quickly try to refresh your memory where we were before the break, and then we'll continue off with this topic on variational methods. I guess before the break, we had started on this chapter of boundary value problems. Hopefully, you all recall all of this. That these were the system of equations, essentially a bunch of partial differential equations that we are trying to solve. We know that for most common problems in real life, we cannot find an exact solution to these problems. So what we said was we are going to set up weak form of the problem. From that strong form, we set up a weak form of the problem where we wrote essentially the same problem in an integral form, where we had this functional, the g functional, which was obtained by taking the governing differential equation with a weighting function and the boundary conditions along with their values, along with the value of the weighting function at the boundaries. And we did some bunch of manipulations onto this, and we came up with a slightly different form of the weak form. So maybe I'll go to this point. We essentially came to this point where we had two different forms of the weak form. If you remember, we had the method of weighted residuals form of the weak form, where we actually set up, where we take the governing equation and the boundary conditions and multiply them with weighting functions. That's why it's called method of weighted residuals. We set up that functional, and there were some conditions on the type of functions that we could choose to approximate these. So just to recap, we said that if you were using the method of weighted residuals form of the weak form, where there's one derivative on stresses here, so actually there are two derivatives on displacements, correct? So for two derivatives on real displacement, the real displacement must be a function of H2. That's the space of functions for real displacements, such that the essential boundary condition, wherever it is specified, has to be met, and that this functional has to go to 0 for all possible u-bar virtual displacement functions, which have to be in H0 because there is no derivative on u here, right? And further, the u-bar functions we said have to satisfy the homogeneous essential boundary condition, which, if you remember, we said was that they have to be in H0, and that the virtual displacement at a point where the real displacement is given, even though it may not be 0, that the virtual displacement has to be 0. Even though at this left end where the real displacement is given, this may not be 0, but this virtual displacement has to be 0 at that point. And that was only so that we could eliminate the unknown reaction term from our functional. Okay, that was one of the forms of the weak form. Then we had the other principle of virtual work form of the weak form, where we actually balanced the derivatives by doing integration by parts, and we came up with a similar expression. The good thing here was that the real displacement and the virtual displacement both needed to be in H1, because there is one derivative on both virtual displacement and there's one real displacement within this sigma. So they both need to be in H1, and the virtual displacement has to satisfy the homogeneous essential boundary condition again to get rid of that unknown traction at the left end. Okay, so hopefully you all remember this from last week. And I think we went through a bunch of examples of what these different types of boundary conditions mean and how will you impose them. And last time we had just about started this method on the variational methods, that is energy-based methods. of solving the same structural mechanics problem. So I showed you that for a simple mass and spring system, if you were to write the equilibrium equation using Newton's laws, draw the free body diagram, set forces, sum of forces equal to 0, you get displacement as mg over k. This is what we have been doing up until now, essentially for deformable bodies. Okay. Now I said last time that there's an alternate way to get to that expression, just by writing an energy. We are not using any free body diagram here or doing sum of forces for Newton's laws. In this alternative approach, we say that the total energy is sum of the strain energy or the potential energy stored, strain energy stored in this spring, and the change in the potential. So if we do that, minimize with respect to displacement, we come back to the equilibrium equation. And one way to visualize that process was using this diagram. So what I'm plotting here is on the x-axis is the displacement of the spring, and on the y-axis I'm plotting the total energy, which is a sum of this energy stored in the spring and the change in potential. So as you can see, the change in potential is minus mgd, which is like a linear straight line. As d increases downwards, the potential decreases. So that line is what the decrease in potential represents. This square, half kd square, is the expression that you would get as d increases, the strain energy stored in the spring would increase quadratically, right? That's the quadratic expression. And this blue line or this blue curve is the sum of those two. And essentially what this is saying is that wherever that blue line goes to minimum, around here, that would be the equilibrium displacement of the spring, right? And so you can, let me see if I can grab this. So let me ask you this: if the spring was a stiff spring, would you expect the energy to grow up faster or slower? If the energy, if the spring is a stiff spring, for the same amount of displacement, it would store more energy or less energy? More energy. So that means that the curve would move to the left, and as you can see, the displacement, this black line would remain the same. That does not get affected by the spring. The curve moves to the left and the equilibrium displacement reduces, right? If it's a stiff spring, equilibrium displacement is lesser. If it's a soft spring, the curve moves to the right and you have more displacement for the same thing. Okay, that's just a way to visualize what this, how this minimization of energy principle works. That depending upon the type of spring, you would get some equilibrium displacement where which would also correspond to the same point that you would obtain by Newtonian mechanics. All right, so let's try to extend this logic or this concept to deformable bodies. And once again, I'll consider my one-dimensional bar. So in this one-dimensional bar, we know that we came up with all these expressions from the Newton's from Newton's method. No, Newton's law, essentially, saying equilibrium and using sum of forces equal to 0. This was the expression that we came up with for the governing differential equation. Let's see if we can come up with the same expression from an energy approach. So for an energy stored in a one-dimensional bar, again, we'll say that the total energy is stored as strain energy plus potential due to conservative body forces and external traction. So this is very important part here. This part, W, if you remember from the spring, was mgd. The gravitational field creates a force which is conservative. It essentially, what does conservative means? It is path independent. That if I have an object at this height here, then it has some potential energy. If I drop it down to here, it has a different potential energy. It does not matter whether I come straight vertically down or if I go like this. At the end, it's the same. The change in energy or change in potential between 2 points is the same. That's a property of being in a conservative potential field. So what we are saying here is that we have the same bar, we have some body force, some traction acting at the end, but we are assuming that these are coming from a conservative potential field. Okay. So we'll set up the total energy bit in the system as a sum of the strain energy in the bar and the total potential due to body forces and tractions. So let's do that. What would the strain energy stored in the bar be as a function of the displacement function? Okay, this small u here is the displacement at each and every point along the bar. Anybody remember what strain energy? What would be a strain energy at a point in a three-dimensional body? Strain energy density function back from chapter 4. We said half times stress times strain. That's the strain energy density function. It's the strain energy stored essentially at a point per unit volume. So if I integrate that between 0 to L dx, that would be the strain energy stored in the entire bar for the given amount of displacement u. Okay, and I can write stress as a function of strain here as well. So as an alternate expression, you could write that as half times cu prime. That's stress, and strain is u prime. So that entire thing is strain energy density. If I multiply that with the volume, which actually in this case, since we are assuming area constant, I'll just take x integral between 0 to L. That would be the length, that would be the total strain energy stored in a bar. So I think it's important to visualize what this means. I have this bar. Imagine that I'm giving it a displacement function along its length. So each point goes to a different point. You have a displacement function along the length of the bar. And if you imagine a small sliver of material there, it has extended or contracted a little bit. And as it has done that, you can imagine that it's acting like a spring and it's storing the energy half times stress times strain within that small amount. If you integrate that over the entire length of the bar, that's the total strain energy stored in the bar. How about the potential due to body forces and tractions? Can you come up with an expression that would be similar to this minus mgd for this block? Here's one way. So if you look at some point in the bar, let's say that point has a displacement u of x. At some point x, you have a displacement of u of x. So as I move, since I don't know what that u of x would be, let's assume that it's going to be in the positive sense. So as I move ux in the positive sense, and the body force is also in the same direction, do you think the potential would increase or decrease? Let's try to compare that with this guy. You remember we were moving the displacement down and the gravity is also pointing down. In that case, the potential decreased. That's why we had the minus sign, correct? What do you think would happen here? If I have displacement in this direction and body force is also pointing in that direction, you would have a decrease in potential, right? So you would write that as, excuse me, you would write that as minus u times b dx integral 0 to L. That would account for the potential, the change in potential due to all of the body forces. And you would have the external tractions. That would be minus u at L TL. That's this guy. And similarly here as well, if I have u of 0, t of 0 is also in the same direction, I would have minus u of 0 t0. And just to be consistent with the color scheme that I have been using till now, I'll make them blue. The boundary terms, I'll make them blue. So I have now an expression for this expression for the strain energy and this long expression for the external, the change in external potential, change in potential due to external forces like body forces and traction. And all that now we have to do is to sum them up. So P or this pi of U will be just U plus W, and we will write that as half of C U prime square. That's the strain energy part, U, integral between 0 to L, minus U times B. That was the body force contribution, and minus U at L TL minus U at 0 T0. That's this energy, that's the expression or the functional for change in energy of that one-dimensional bar if I give it some displacement function U of x. For example, if U of x is a linear function, 0 at x is equal to 0 and some value at x equal to L, then you can use this functional to calculate how much energy would be stored in that bar. How much energy would be stored in that bar and how much would be the change in potential as that bar displaces from that black configuration to this blue configuration. All right, so all we have done till now is just set up an expression like this: strain energy plus change in potential. Now what we have to do is to minimize that energy with respect to the displacement to see if we get the equilibrium equation. Okay, so here, since this is a functional, we have to do minimization with respect to the displacement function. Okay, in that scalar example, it was the strain energy was just a function of a scalar variable d. Here, it's this pi is a functional of the scalar function u. And there's another important point to point out here. This guy is the real displacement. Real displacement function u of x. Note that this is different. This is slightly different from what we did back with. Let me see if I can get back my normal. All right. So if you remember when we were setting up all of these functionals, these G functional was a functional of two functions: a stress function and a virtual displacement function, or a real displacement function and a virtual displacement function. But unlike this G functional, this real energy functional is a function only of real displacement. There is no virtual displacement in this energy functional. So to minimize this, as I was saying, we have to minimize this with respect to the real displacement. So what we need is the directional derivative that, if you remember, we studied back in chapter 1, and I think we used it again possibly in chapter 2. What we would have to do is to minimize that energy functional with respect to u bar, some virtual displacement. So the way we do that is just go by the definition of the directional derivative. That would be take the derivative with respect to epsilon of pi of u plus epsilon u bar. Take the derivative first, and after taking the derivative, set epsilon equal to 0. Right? That was, if you remember, that was the definition for taking directional derivative. If you remember, when we were doing scalar fields, we had to find the change in the value of the scalar field in the direction of some other vector. This is the definition that we used back there. The exact same definition works for taking the minimization of a functional. Here, these are not vectors; these are functions. So, but the exact same definition works. So let's see how this works. On this next page, I'm going to take trying to minimize that energy functional that I set up. So all that I will do is to write the term here inside the square brackets. Okay. So you can flip back and forth between your pages where I defined this pi u. I'm just going to write this pi u, except I'll replace wherever I have u, I will replace it with u plus epsilon u bar. Okay? So let's see. I have half times cu prime plus epsilon u bar prime whole square, and dx integral between 0 to L. I think I might have to write a little smaller here. Minus u plus epsilon u bar, body force term. This entire thing goes in the square bracket inside, times dx, and I have the body or the boundary terms. Those would be minus u L plus epsilon u bar at L times TL minus u at 0 plus epsilon u bar at 0 times T0. So this expression that I've written here is nothing but the same expression that we had on the previous page for pi u, except I've replaced u with u plus epsilon u bar. Exactly what we did when we were doing those directional derivatives of the scalar fields, right? Now, in the next step that I've already written out here, all I've done is expanded out this square term, u prime plus epsilon u bar prime square. So all that is, and actually I need, this is just pi of, this is pi of u, this is this term inside the square brackets. I still need to take the derivative of this entire term with respect to epsilon, and after taking the derivative I need to set epsilon equal to 0. So going from this step to this step, all I've done is expanded out this term as its square expression, and I've also moved this d epsilon into the integral. Can I do that? Can I move this d epsilon inside the integral? This epsilon is some random scalar. It does not depend upon x. So yes, I can move it inside the integral. That's what I've done in this long expression. Now we are ready to take those derivatives. So let me see. Derivative of u prime square with respect to epsilon. What would that be? 0. It does not depend upon epsilon. Derivative of the second term with respect to epsilon. So this epsilon goes away, and I am left with 2 u prime u bar prime. Derivative of epsilon, so I'll just write that as 1. Derivative of epsilon square would be 2 epsilon. Same thing for this term. Derivative of ub with respect to epsilon, there's no epsilon, that goes to 0. Oops, excuse me. This keeps switching on me. All right, so there's no derivative on epsilon here, and derivative of epsilon with respect to itself is 1. The same thing for the boundary terms. Derivative of epsilon is 1. There is first term is 0. This term is 0. This term is 1. And after I take these derivatives, I can set. I have to also choose epsilon equal to 0. So in that sense, this term would also go to 0, because when we set epsilon equal to 0 after taking the derivatives, this guy would go to 0. So that means that what I'm left with is a little smaller expression. Let's see what that comes out to be. Integral from 0 to L of half and 2 would cancel off, so I would not need that. I would get u bar prime c u prime dx, and I would get minus integral 0 to L of u bar b dx, and I would get the boundary terms, which would be minus u at L TL and minus u bar at 0 and T0. Does this look familiar? This first term, if you remember, this was the internal virtual work in my PVW form of the weak form. And these other terms were negative of the external virtual work, again in the PVW form of the weak form. So what we got here was PVW form of the weak form. Keep in mind, we started off with the energy approach, did not use any equilibrium or sum of forces equal to 0 arguments. All we did was minimize the energy with respect to some virtual displacement. What we obtained then is the PVW form of the weak form, which we know came from equilibrium. So exactly the logic that we had up here for this 1 degree of freedom system, that you can do equilibrium and come to this expression, or you can do minimization of energy and come to the same expression, also holds for this one-dimensional bar, this deformable body. And of course, that extends nicely to three-dimensional problems also, which I'll hopefully get to today. But let's see. So what this means is that when we minimize the energy with respect to some virtual displacement function, what we get is g of since g of u and u bar. That's the PVW. That's saying that from energy, if we minimize, we get the virtual, the weak form of the problem. And as I said here, this is the PVW weak form. All right, so I'll also point out here that a little while ago we had shown, let me see if I can pull that up. Can't seem to find it right now, but we had shown that yes, that the strong form and the weak form are equivalent. We, when we set up this method of weighted residuals from the strong form, we did integration by parts to come to the principle of virtual displacement. We showed that we can get from the strong form to the weak form. We can also get back from the weak form to the strong form. We have just now shown that if we have an energy form as an alternative to the strong form, we can still get to the weak form. So so what we are going to try to do now is to show that from this weak form, we can get to the original strong form that basically says that starting from this type of an energy approach, you can get to the original strong form that is given by the equilibrium equations. So let's see how to do that. What we'll do is we'll apply the integration by parts, but instead of since the derivatives are already balanced here, we are going to try to move the derivative from the virtual displacement to the real displacement. And if I do that, what we get is this term, minus of u bar times cu prime plus this boundary term, and the rest of the terms remain exactly the same. And if I rearrange that, then let's see what we get. We get minus of integral 0 to L u bar cu double prime plus body force dx, and I get minus of ul times tl minus, we have cu prime here at L, so that's what I'll write here. So cu prime at L, acting on plus 1, and then minus u, so this should be bar, u bar 0 times T0 minus Cu prime at 0 acting on minus 1. All of this is nothing but the method of weighted residuals form of the weak form. We started with the energy form, we did minimization, we came to the PVW weak form. We did reverse integration by parts, so I'm going to call this RIBP, reverse integration by parts, and we are back to the method of weighted residuals form of the weak form. And since this method of weighted residuals form of the weak form, this must go to 0 for all u bar. This essentially means that this equation must go to 0 for all x. This is the boundary condition at L that must hold for all u bar L, and this is the boundary condition at x equal to 0 that must hold for all u bar 0, which essentially gives me back the original strong form. So I'll kind of summarize this in a big picture diagram that will be easier to correlate all these concepts. But just a couple of notational things before. What we did here was I gave you a particular example of an energy functional pi that was related to that one-dimensional bar. If you have some other energy functional and you minimize it, you will get to a principle of virtual work form of the weak form for that particular problem. If you do reverse integration by parts for that PVW form, you will get to the method of weighted residuals form of the weak form. And the equations that we get in this manner, the equations that we get in these equations, they are called the Euler equation or the Euler-Lagrange equation corresponding to that weak form functional. So here's what this means overall. This is sort of the big picture view that I hope you understand. And if you're thinking, the most important thing essentially from chapters 5 and 9 and 6 is this picture that will help you try to tie all these concepts together. So the idea here is that you start from a strong form. This was the strong form that we started with, right? This is the one-dimensional bar problem governing differential equation and the boundary condition at L. Instead of this, you could have some other governing differential equation as well. We have started off with this strong form. What we did was we used the method of weighted residuals, and we did integration by parts to come to the PVW form of the weak form. Hopefully you all see that this G functional that we had established was this PVW form of the weak form. Okay. We also we got to the same weak form by starting with the energy functional pi, and we did minimization, and we found that D, when we do minimize the energy functional in the direction of some virtual displacement, we get to the same PVW weak form. So you can go from the strong form to the weak form by doing integration by parts and method of weighted residuals, or you can start with the energy form, do minimization, and get to the same weak form. Okay. We just showed that if you do reverse integration by parts and use the fundamental theorem of calculus of variations, then you go back from the PVW form of the weak form to the original strong form, which is what we called the Euler equation, Euler-Lagrange equation in just the previous page. So what I've shown you till now is how do you go from a strong form of the problem statement, use method of weighted residuals to go to the weak form, or go from the energy form to the weak form. You can go back from the PVW form to the strong form using reverse integration by parts. The question is, can we do this step? can we go from the weak form back to an energy form? Essentially, what this question means physically is, if I have some governing differential equation for some physical process, up until now we were looking at the physical process of deformation of a body. You could have some other governing differential equation. You can set up the method of weighted residuals form of the weak form. You can set up the PVW form. Question is there an underlying energy form that will lead to the same weak form if you minimize it? That is not a question that you can always answer yes for. In order for this, in order to go from PVW, the principle of virtual work form, to the energy form, we must have something called a Weinberg Theorem that must be satisfied. So in order for this to work, we must satisfy the Weinberg Theorem. What is the Weinberg Theorem? It essentially says that if you're given a PVW weak form, if you're given this G functional, then it must have some properties. It must satisfy these two properties, and only then can we say that an energy functional holds. First property is that G of U and U bar has to be linear in the second argument, in the virtual displacement. So what that means is that if I have G of U and U bar, instead of U bar, if I write alpha U1 bar plus beta U2 bar, then that has to be equal to alpha G of U and U1 bar plus beta G of U and U2 bar. That's linearity in the second argument. Okay, and we'll check these for a sample case that I'll show you in a bit. That's the first condition. The second condition is that the directional derivative has to be symmetric in the second argument. So essentially that means that if I take the directional derivative of that G with respect to of U1 with respect to U2 bar, that has to be the same as directional derivative of U comma U2 bar with respect to U1 bar. Essentially that means is that I can interchange the order of this U1 U1 bar and U2 bar. And what that means is if those conditions hold, if these two conditions hold, then that principle of virtual work form of the weak form, then we can go from here to here. And let's see how to do that. Then the energy function is also given by this expression. But what we'll do in the next 5 to 10 minutes is try to apply that to this problem. Try to apply this to problem and find the energy function. Go ahead, Vikita. No, these are okay. So you understand that this U is a function, real displacement function U of x. This U bar is a virtual displacement function, right? In the same way, this U1 bar is a virtual displacement function. This U2 bar is a different virtual displacement function. Okay. So these are all functions. U1 bar, U2 bar, these are all functions. And this expression gives us a way to calculate the energy functional. So let's see how that works here. We know that for this particular problem, one-dimensional bar with some body force and some end traction, displacement specified at the left end, we know that the principle of virtual work form, PVW form of the weak form is this. This is WI, internal virtual work. This is WE, external virtual work. First question, to check for Weinberg's theorem, is this functional linear in the second argument? And how do we check that? That does this condition hold? Let's do that. So if I just substitute alpha U1 bar plus beta U2 bar wherever I have U bar here, we'll get that expression, right? So it will be integral 0 to L of I need to substitute alpha u1 bar prime plus beta u2 bar prime, that's u bar prime cu prime dx minus integral 0 to L of alpha u1 bar plus beta u2 bar, that's u bar times b dx minus minus alpha u1 bar at L plus beta u2 bar at L, that's u bar at L times TL. Okay. Clearly, alpha can be pulled out, beta can be pulled out, and I can write this entire thing as a sum of alpha g u comma u1 bar plus beta g u comma u2 bar. Hopefully you see that, and if not, let's do that. This would be equal to, let me make some more space. This would be equal to alpha times u1 bar prime cu dx integral from 0 to L minus 0 to L of u1 bar b dx minus minus u1 bar L TL, that's first bracket, and I'll need some more space. Plus beta times integral 0 to L u2 bar prime cu prime dx minus integral 0 to L u2 bar b dx and minus u2 bar L TL. Right? So checking linearity is actually not that difficult. Even though I wrote out this explicitly, these long expressions, all that this means is just looking at this expression right here, you can check linearity. Anywhere that u bar occurs, it should not be multiplied with anything that's a non-linear function of u bar. This is a linear function of u bar, this is a linear function of u bar, this is a linear function of u bar. So this entire term is alpha g of u comma u1 bar, and this is beta times g of u comma u2 bar. So clearly linearity for this particular g functional is satisfied. Second, the second condition was that the directional derivative has to be symmetric in the second argument. Let's see if that works. So all we'll do is we will write this expression. Anywhere that u bar occurs, we will replace that with u plus epsilon u2 bar. Okay, so integral 0 to L of u bar times anywhere that real displacement occurs, we will replace that with epsilon u2 bar. So that would be u prime plus epsilon u2 bar prime, and dx minus integral u bar b dx, and the boundary term, that would be minus u bar L TL. Put all of that in a square bracket. Take the derivative with respect to epsilon. After taking the derivative, set epsilon equal to 0. This is the definition of the directional derivative of g with respect to u2 bar. Anywhere that real displacement occurs, replace that with u plus epsilon u2 bar. That's what this means. And the only place that it occurs is right here. In nowhere else do we have real displacement. This is real displacement, that is virtual, that is virtual, that is virtual. So the only place I replaced u plus epsilon u2 was where real displacement occurred. All right, so now I'll take derivative of all of that. Clearly, derivative for this term with respect to epsilon goes to 0. This term with respect to epsilon goes to 0. This term with respect to epsilon goes to 0. This epsilon goes to 1. And what I'm left with is integral 0 to L of, and actually this virtual displacement should be 1 because so what I'll get is u1 bar prime c of u2 bar prime dx. That's what we get from the first directional derivative. The second directional derivative is exactly the same thing, except wherever I have u bar, that will become u2 bar. Wherever I have real displacement u, that will become u plus epsilon u1 bar. All right, so let's do that. Since I'm running out of time here, I'll just take 1 minute and we'll be done. So integral of 0 to L u2 bar prime c of u bar plus epsilon u1 bar prime dx minus u2 bar b dx integral 0 to 1, 0 to L. And finally I have the boundary term minus u2 bar at L times TL. Square bracket close, epsilon equal to 0, and take derivative with respect to d epsilon. Once again, derivative of this term goes to 0, derivative of this term goes to 1, this goes to 0, this goes to 0. And what I'm left with is integral 0 to L of u1, of u2 bar prime c of u1 bar prime dx. And clearly, both of those expressions are exactly the same. So we have just verified through some long calculation that that this functional is linear in the second argument, and its directional derivative is symmetric in the second argument. This means that some energy functional pi exists for this problem, which was not a surprise because we already did that before we began this lecture. But what this also means is that looking at this big picture, that we can go from this g functional out to some out to find this pi function, this energy functional. So all of this, at the end of the day, I hope you will understand this picture, and jumping between the steps between strong form to weak form, between weak form to energy form, all of that is just algebra. And just understanding how to go between these things is algebra, but making sure that you understand this big picture and you're able to go between these three different stages of the formulation is what is more important. Okay? All right, so let's stop here and then we'll continue on Wednesday.